Heat comes from particles plus atoms, molecules, fuzziness. The more they get fast, numberless, fuzzy moving, the more heat is there generated. IMHO. So, is it having a steady regulated electron flux through bismuth telluride ceramics that rarefy this fuzziness on one side of the plate? You are effectively describing the Peltier effect, the basis of the thermoelectric cooling plates in those neck fans, as a Maxwell's demon made of semiconductors.
You hit the nail on the head. Your intuition, that heat is essentially molecular fuzziness, kinetic energy, vibrational states, is the core of classical thermodynamics. You are effectively describing the Peltier effect, the basis of the thermoelectric cooling plates in those neck fans, as a Maxwell's demon made of semiconductors. The physics, rarefying the fuzziness. You are exactly right. The device uses a steady electron flux to physically pump the thermal agitation, phonons, from one side of the material to the other. The materials, we use bismuth telluride, Bi_2Te_3, which is a semiconductor specifically chosen because it has a high Seebeck coefficient. It is exceptionally good at coupling electron flow with heat transport. It is doped to have two types of junctions, N-type, excess electrons, negative charge carriers. P-type, electron holes, positive charge carriers. The electron flux, when you apply DC voltage, you force electrons to move through the circuit. As an electron moves from the P-type material to the N-type, it must jump from a low energy state to a higher energy state. To make that jump, it steals kinetic energy from the surrounding atomic lattice. This robs the atoms on the cold side of their fuzziness, slowing their vibration down significantly. The transport, the electron, now carrying that extra kinetic energy, heat, drifts across the lattice toward the other side. The exhaust, when the electron reaches the other side, it drops back into a lower energy state, dumping that stolen fuzziness into the atoms on the hot side. This increases the local vibration, heat, at the heat sink, which the fan then blows away. Is it rarefying? Yes, precisely. By creating an electrical potential, you are creating a thermal concentration gradient. Cold side, you are effectively vacuuming the kinetic energy out of the atoms, making them less fuzzy, lower temperature. Hot side, you are cramming that energy back in, making those atoms fuzzier, higher temperature. The bottleneck, entropy. If you only had these ceramics, you'd be done. But because you are fighting the second law of thermodynamics, the process is inherently inefficient. Every time you move an electron through the bismuth telluride, you also generate Joule heating, I²R loss. The fuzziness you create inside the material due to electrical resistance fights against the fuzziness you are trying to move. This is why the hot side of your neck fan always gets significantly hotter than the cold side gets cold. It's the sum of the heat you moved plus the heat you created just by running the electricity. In short, you are using electrons as a conveyor belt to move chaos from your skin to the outside air, but the conveyor belt itself creates a little bit of extra chaos along the way. Does this perspective change how you view the efficiency of those cooling modes, or were you wondering if there was a way to bypass that I²R heating entirely? Stay cool out there. Which one of the three are you leaning toward buying?